Now, in this lecture, we will talk about the net capillary filtration rate and the significance of it. So this lecture is almost a concrete example of the context we discussed in the last two lectures. So there is no new physics in this lecture. It's more about like application. And previously we discussed that the volumetric flow rate from capillary to interstitial space, from capillary to interstitial fluid. It is given by LP multiplied by S multiplied by the psi in the capillary subtracted by the psi in the interstitial fluid. And recall that psi is the chemical potential of the medium, which is hydrostatic pressure minus the osmotic pressure. So this equation you can also write as okay. Now let's look at some data about a typical capillary. And so we are going to directly use the real data to figure out the direction of the filtration. So what I'm putting here is a table set showing the numbers or properties of capillary. So everything here is about capillary. So the inside diameter, so let me draw a capillary. Oops. Here I'm drawing a capillary. The inside diameter means this is 10 micron. The length is the length of a typical capillary. Wall thickness is the thickness of the capillary wall, or the thickness that is contributed by the endothelial cells, and the basement membrane. So I'm just drawing this. This is the thickness of the wall. And the average blood velocity means the average velocity. Pore fraction is the area of the pores on the capillary wall compared to the lateral area of the capillary. Wall pore height, so here we assume it's a slit, rectangular slit. So this height is the total height on 2H. We'll write it. That's it, terrible. So now for the capillary, we know that they are connected to the artery. So then they exit. So here is this side is considered as inlet. Now this is also the arterial end. And this part, and when blood leaves the capillary, this is considered as outlet. Now this is the venous end. So the hydrostatic pressure at the inlet is higher than the hydrostatic pressure at the outlet. And this is because it's a pressure, we have a pressure drop, and because of viscosity, the pressure decreases along the way because of the viscous dissipation of the energy of the fluid. So if you ask what's the mean hydrostatic pressure, like as a whole, then it give you a number 17.3 millimeter mercury. And for osmotic pressure, we assume it's uniform, so there are no inlet-outlet difference. So this is inside the capillary. Maybe let me put the capillary inside of the capillary so that we don't confuse it with interstitial space. So this is capillary. Outside of the capillary is interstitial fluid. And the interstitial fluid, it's also assumed it's uniform to give you a hydrostatic pressure, which is negative. It means it's compared to some gauge pressure, if you're thinking that way. This negative is also, you can see in a dramatic big contrast with the hydrostatic pressure within the capillary. And also we assume a constant interstitial fluid osmotic pressure. And you can see the osmotic pressure within the capillary is higher, 20 millimeter mercury, higher than the osmotic pressure in the interstitial fluid. This is because of the protein retention we discussed in an earlier lecture. And although there are more proteins inside of the plasma than that in the interstitial fluid, this is because some big proteins cannot leaving the capillary due to their size limit. And you also notice that here we use, in the table, it uses millimeter mercury as a unit for pressure. So you can convert a millimeter mercury. You can just like calculate it on your own, verify it on your own. I'm just going to tell you 1 millimeter mercury is equal to 133.322 Pascal. If you want to convert it to SI units, that's how you convert it. Now, the first thing we are going to do is using the equation for the volumetric flow rate, basically this equation. And then let's figure out what's the direction of the flow at the inlet versus outlet. So since Q, just write it again. It is equal to LP as delta plus I. So delta plus. So the LP and the S are both positive. So that means the sign of S or the direction of the flow is determined by delta plus I. So if you have delta plus I greater than 0, since delta plus I is defined as capillary multiplied by, capillary subtracted by the interstitial space, let me write it. This is defined by the capillary subtracted by the interstitial space. So if this is greater than 0, it means your Q is greater than 0. So that means the filtration flow, you have flow from capillary to the interstitial fluid. On the other hand, if you have delta plus I being less than 0, then you have Q less than 0. Then we have flow from the interstitial fluid to the capillary. Okay, Now knowing this, let's look at the sign. So let's calculate delta per psi at the arterial end. So by using the numbers in the table, we need to calculate PC minus P interstitial fluid subtracted by IC minus I interstitial fluid. Let's look at the table. Oh, by the way, it's better that you keep this table in your notes, or you can write it out down, because for the homework exercise, and also for some part of the rest of this course, there will be some point we needed to go back to this table. Basically, we needed to use the number in this table to work on problems. So it's good to just keep this table. So let's see, PC at the inlet is 30 millimeter mercury. And then PIF is minus 3 millimeter mercury. You minus high C minus high C, which is 28 millimeter mercury, subtracted by PIF is 8 millimeter mercury. So if you just calculate the numbers, you will find that this gives us 30 millimeter mercury. So it's a positive number. So that means at the arterial end, the filtration happens from capillary to the interstitial space. Now let's look at the venous end. The same thing. Let's look at the table. So we have 10 millimeter mercury subtracted by minus 3 millimeter mercury. Subtracted the same thing. 28 millimeter mercury subtracted by 8 millimeter mercury. It give us minus 7 millimeter mercury. So it's less than 0. Physiologically, what does that mean? It means you have a capillary. So here is your arterial and the venous end. So the filtration actually happens at the beginning of the capillary. The Q is from inside to outside. And at the venous end, we have Q from outside to inside. And this is actually something like physiologically significant. This is called like the Starling flow. So what you have is you have filtration. This is filtration, and this is called reabsorption. And this cycle is called like you have outward flow and then back inwards continuously. And this type of behavior is called the Starling flow. So you may wonder that there are outflow at the beginning of the capillary and and inflow at the end. So on average, like what's the net? So does it on average that the capillary filters fluid outside to the interstitial space, or on average it absorbs more? So we can calculate what's on average. So to calculate the average, what you need to use is this mean hydrostatic pressure. And the rest of the numbers like doesn't change. So let's calculate the average. Do you have 7.3 millimeter mercury minus 3 millimeter mercury? And then you subtract 28 millimeter mercury minus 8 millimeter mercury. To give you a number slightly positive. So on average, there is a net filtration into the interstitial space. So on average. Net filtration into the interstitial space. Like in terms of how much, so the reabsorption accounts for 90% of reabsorption. So for all the fluid that is filtered at the beginning or at the arterial end of the capillary, 90% of them get reabsorbed. And 10% of them go to the enter into the interstitial space. Then what happens to the 10%? They cannot keep on accumulating in the interstitial space. If you have like keep on this accumulation, then you would expect edema. So, but that doesn't happen under physiological conditions. So those are actually drained into the lymphatic system. So they will enter into the lymphatic system, and then eventually go back to the blood. So this is the cycle. Okay, let's see. I think that's all I would like to cover. So you want to do an example? Okay, maybe let's do an example. So let's think about what's the net filtration for a human body. You may wonder, okay, I have the data for a segment of capillary, but in the body there are so many small capillaries. Like, what's the net rate of filtration? Maybe that's what a question you can ask. So let's calculate. Calculate the normal rate of net filtration for the human body. Assume the total capillary area. So total is 500 meters squared. So this is all the capillary, the area of all the capillary in the body, not just one segment. Now let's assume tortuosity. Of the slit force is true. And let's assume Newtonian fluid and with a viscosity, so plasma modeled as a Newtonian fluid. With viscosity 1.2 times 10 to the minus 3 Pascal second. Okay, so the rest of the parameters will come from the table we show at the beginning of this lecture. So in order to find the total volumetric fluid across all the capillary walls, we will use this equation, SLP and the delta psi. Now, let's figure out what is delta P. Delta P or delta psi. So previously, let's see, we calculated on average delta psi is 0.3 millimeter micron. So we calculated what psi is 0.3. And if you convert it to like SI units, it's about 40 Pascal. And we know the area is 500 meters squared. Now let's figure out what is delta. LP is, we have the equation for rectangular pores. It's epsilon, which is squared divided by divided by 3 mu L. Now let's collect the number from the table. And here we have been told that the porosity is 0.001. Do we have the porosity? Oh, porosity is in the table. Yes, porosity is in the table. 0.001. H is the height. So from the table, the true height is, well, H is half height. The height is 3.5 nanometer. Sorry, the height is 7 nanometer. That the half height is 3.5 nanometer. 3. Mu viscosity is given in the problem statement. The tortuosity is true. The length of the pore is the thickness of the capillary wall, which is 500 nanometer, which is 0.5 micron. So which is 0.5 micron. Okay, if you put these together, you will find the hydraulic conductance of our capillary wall is this. Now we can calculate what is Q. Q is S the area is 500 meters squared. LP 3.4 times 10 to the minus 12 meter squared Pascal. And we have pressure of the chemical potential difference. Or we can just put the total pressure difference, 40 Pascal. And then put it together, it will give you 6.8 and times 10 to the minus 8 meter cube per second. That's the rate of filtration in the body. That amount happens like per second. This amount happened all the time in the body. You can think about it. This is what happened right now in your body while you are listening to this lecture. Okay. Let me leave some exercise for you guys. So this is an exercise. So capillary design optimization. So you have an artificial capillary, and it is give you these properties, and also have you design constraint. If you want to maximize this volumetric flow rate, how do you choose your designing? Like, how do you choose your pore slit height? How do you choose the porosity and the wall thickness? Let's look at second exercise. So for this lecture, we have leave two problems for you to work on.